It's just kind of hard to see the left forward.
Oh,
This guy right.
but the problem is,
I won't be sending it anyway.
is this?
So
I think someone.
Billy's gonna, I think the two, me and Billy are sitting there.
Okay.
Quentin's sitting there.
I'm sitting there. You can sit there. Yeah.
That's like the worst thing. Might want to.
We can sit at the back.
Yeah.
Yeah, but it's most of them are like.
I just.
Very. I think I'm not the ones that I did. Yeah. I mean,
That he mexeu toda ela fez. I think that was it.
You know, I put him on the field here. He's like field there.
yeah, I don't know.
He's my undergrad.
Yeah, I agree. Oh my god.
Yeah, you're my grad.
It's just straight amount.
Alright, this will be cool. Fine.
I can send it.
I'll wait till it's literally. Stop for a second.
Title of your lecture. Higher forms.
Getting higher. Yeah, science are going for it.
I like
No, I saw that you had something. And someone had something. Yeah, it's like, okay, maybe I should. Yeah. Whenever you're ready.
Okay, welcome back. So our next lecturer is Ho-Tat Lam. Ho-Tat is wearing the 2019 Tazi t-shirt, but Ho-Tat was here as a student in 2019. So I hope that all of you have such a fast turnaround from student to lecturer. It's a good pipeline. Ho-Tat will tell us about getting higher form symmetries and their application. Getting higher has multiple interpretations in Boulder, I think.
That's right.
Altitude.
Yes.
Yeah, just the altitude. Yeah, exactly. That's it's a mic working, just to make sure.
Is the green light on?
Just to make sure. Yeah, it's on.
Okay.
So it's okay. Good. Yeah. So I was a student at 2019, and at that time Clay was my teacher actually. So yeah. Anyway, so so the lectures will be about higher form global symmetries. And let me just start with some opening remark. So if you look back in history, symmetry has been a fundamental principles in theoretical physics. A lot of progress was made because we identified some hidden symmetries in the systems, and we use those symmetry in a wise way. And since we're dealing with relativistic quantum field theories, so we know that the type of symmetry, the structure of symmetries, are actually strongly constrained by Coleman-Mendula theorem. And of course, there are some exceptions, like, for example, supersymmetries and conformal symmetries. And today, the kind of symmetries that I'm going to tell you about is higher form global symmetries is yet an exception of Coleman-Mendula theorems. And the reason why it evades the usual Coleman-Mendula theorem is that this is unlike the usual symmetries. These are symmetries that are, in some sense, generalizing the symmetries that we are familiar with. So in what sense is generalizing the symmetries that we are familiar with? It is in the following sense. So these are symmetries that acts only on extended operators. So usually when we think about quantum field theories, we think about some point-like operators. But then there are also extended operators, like line operators, surface operators, and so on. So higher form symmetry is a symmetry that governs these extended operators. And in these extended operators, when they act on the vacuums, they can create extended states as well. So they don't act on particles, they act on strings, for example, and membranes. So this is the nature of this kind of higher form global symmetries. So the plan of today's lecture, of the coming 4 lectures, is the following. So I'll first start with free field theories. So the title is called Fun with Free Field Theories. So this is something that we're all familiar with. And then I'll start with something that we're familiar with and start building up some knowledge and concepts. And then in particular, we'll introduce something about higher form symmetries in the context of free theories and various notions related to symmetries. And from what we have learned from that, then we'll get into the meat. So these higher form symmetries are particularly important and useful for at least two contexts. One is the study of gauge theories, and the other is the study of topological phases of matters. So if I tell you these two topics, the first thing you might think about is that this is coming from two completely different communities. One is gauge theory is usually discussing high-energy theory, well, topological phases are usually discussed in condensed matters. But as you will see that these days, higher form global symmetries actually give you an umbrella that unifies both and connects both the high energy communities and condensed matter communities. And in fact, there's a lot we can learn from each other. So that will be one of the things of these lectures that will draw lessons from both high energy sites and condensed matter sites. And another important thing of this lecture is the following. So one of the main takeaway of the lectures is that it's very important to think about topology in quantum field theories. So this is one thing that I hope that you can take away from is that there's a lot of use of topologies in the study of quantum field theory, not just in topological quantum field theories, but also in conventional quantum field theories. And in some sense, the topic of symmetries is the topic of topology. And I will show you why this is connected. And the second main lessons or main thing to take away is that it's important to think about quantum field theories in terms of operators, not just in terms of some fields and some path integral, but in terms of some operators. And when we think about quantum field theory in terms of operators, it's important to not just think about point-like operators, but also extended operators. So that's another key message. And if we talk about extended operators, they can also be extended defects, for example. Okay, so these are two big messages that I wish you would get from the lectures. Okay, so let's start with something concrete. So let's start talking about free field theories. So what is the simplest free field theory one can think about? So the one I'm going to talk about is basically a compact boson. So I'll be working in d dimensions. So big D is representing the space-time dimensions. I'll use little d to represent the space dimensions, just to not be confused. So what is a compact boson? A compact boson is a real scalar with a periodic field strength, a periodic field range. So I'll always work with canonical normalizations where phi is 2π periodic. So what is a Lagrangian? The Lagrangian is basically a free theory of Lagrangians. It's a quadratic free Lagrangians. And one thing to emphasize is that I put in this coefficients, which usually are not there if we study non-compact bosons. But this coefficient is actually important. So this coefficient is meaningful because I fixed the normalization of phi to be 2π periodic. So that means that I cannot redefine phi by rescaling it to absorb R into phi. So that's why this is a meaningful constant. And this is a constant that is dimensionful. Its dimension is generally given by d minus 2 over 2. So this Lagrangians is probably one of the most common Lagrangians that you will see in physics. It appears in many, many different contexts, both in high energy and condensed matter. So for example, in 1+1 dimensions, because this parameters is actually dimensionless, so they describe conformal field theories. And they actually appears in physical systems. They describe one-dimensional electrons with strong interactions, which give rise to what's called a Ladinger liquid. In 2+1 dimensions, they describe the low energy physics of superfluid, which was discussed in Zohar's lectures. And in 3+1 dimensions, they have an even fancier name. They are called axions. So they are discussed in particle physics context or in string theory context. So this will appears in Nathaniel's lectures when he discussed the formal aspect of elementary particles. Okay, so yeah.
When you say they, it means you're parameterizing these theories by the R, like that they mean several theories and each of them are labeled by R.
That's correct. That's correct. So R parameterize different theories, and they have different physical meanings. So for example, here R means the radius of compact bosons. Here it means it gives rise to what's called superfluid stiffness. It's a physical parameters that you can measure, and this is related to axion decay constants. Okay, so this R is meaningful. Good. So the questions we would like to ask is that what are the global symmetry in the theory? Okay, but let me put in constraints. So let's just talk about global symmetry that acts on the field phi. Okay, so what are the global symmetries? Is there any? Yeah, that's right. There's translations. Okay. Other? Yeah, that's right. Yeah, so there's a shift symmetry. With shift phi, but it can just not be +1. It can shift it by some arbitrary constants. And because phi is periodic, so this constant take circle values. So this is in fact a U1 symmetries. Okay. Any more symmetries? Yeah. Someone mentioned Z2 symmetries. That's right. Just a Z2 charge conjugation symmetries. That shift phi to -phi. Someone was saying something? Oh, okay. Yeah. Yeah, so in fact, there's also, of course, the Poincare symmetries that the translation is embedding. Okay? So these are some symmetries that act on phi. But the questions, the things I would like to point out is that, is this all the symmetries that exist in the theory? Okay? So to answer this, let's actually go to something that's more important. That's also very important. Another concept that's very important. This is the notion of dualities. So duality is probably one of the most deep and fundamental concept in quantum field theories. So what is duality? Duality, roughly speaking, means that if we give you two Lagranges, they describe two separate quantum field theories, quantum field theory 1 and quantum field theory 2. Okay? They look distinct, but then secretly it's possible that they describe the same physics. So this is a notion of dualities. There are tons of dualities in the literatures. There's T dualities, there's particle vortex duality, ADS-CFT dualities, and so on and so forth. So today we're going to consider one such dualities, which is T dualities in 1+1 dimensions. So so far the discussion is in general dimensions, but now I'm going to restrict to 1+1, unless I say I'm changing the dimensions. Okay. So we're in 1+1 dimensions. So you can write that actions in a different way. So the way you write it is that you write it as you introduce a new vector field x mu, and then you write it this way. Okay. So this is the quadratic actions in x mu. So that means that we can integrate x mu, right? So if we integrate x mu, the equation of motions tells us that x mu is given by minus 2 pi I r squared partial mu phi. Okay? And if we substitute it back, we just recover the same Lagrangians. Okay? So this is just a rewriting of the Lagrangians that we start with. But now there's another thing we can do. You see, phi appears linearly now, so we can integrate phi. So what happens if we integrate phi? So phi's equation of motions tells us that partial mu x mu equals to 0. Okay? So then we can solve it. So there's an obvious solutions that is given by x mu equals to partial mu nu theta. Okay? So this will automatically solve these equations by the Bianchi identities. So if we substitute it back, then what we get? Then we get basically a new Lagrangian that is written in terms of theta. Okay? And the new Lagrangians will now have a different radius, which is given by 1 over 2 pi r. Okay? So this is the content of T-dualities. So what is T-duality? T-duality is basically saying that a compact boson in 1 plus 1 dimensions is self-dual to itself, but then the dualities actually change the radius, map radius r to 1 over 2 pi r. Okay? So this is what's called T-dualities. But then if you pay attention to what I said just now, I said the word compact boson. I was saying that this field theta is a compact boson field. But I didn't show you what is the periodicity of theta. Okay? So let's talk about what is the periodicity of theta. So this is the subtle things. The way we'll do it is that let's make our space-time a torus. Okay, so we will work with the torus. So this is the time directions. So this is big T, and this is the x directions, which is given by big L. So this and this are identified. This and this are identified. Okay, so we're working on torus. So on this torus, we can consider the following configurations, where phi, remember, is a periodic scalar. So when it goes around a circle, it doesn't need to come back to itself. It can come back to itself up to 2 pi times the integers. So that means that I have winding configurations where my phi takes the following value, 2 pi n times x, where I require n to be integers. So that when phi comes back, it comes back to itself up to 2 pi. Okay? So this is an example of winding configurations. So now let's substitute this back to the Lagrangians. So the action is now include, let's just focus on these terms, okay? So these terms, so this term is given by x mu, partial mu, phi, integral of dt ds, okay? So let's just substitute this phi into here. So if we substitute it back, then what we get is that we get an expression like this. Oh, by the way, there was one thing I forgot to mention. Throughout the lectures, I always work with Euclidean signatures. So if you see some I's, there's a reason. It's because I'm working in Euclidean signatures. Okay, so this is what happens if we substitute winding configurations into the expression here, okay? So now, you see, n can take integer values. So if I sum over all possible n, then that means that this thing has to be quantized. So this tells us that integral of x1 dt has to be quantized. But what is integral of x1 dt? Integral of x1 dt, if we use these equations, is basically integral of minus time derivative of theta dt. Okay. So since this is 2 pi periodic, then that tells us that theta can wind, right? If you theta winds, then it can give you something that is 2 pi times integers. So this tells you that theta exactly have the same periodicity as phi. It's 2 pi periodic, so it's canonically normalized. Okay. Good. So because this is canonically normalized, so that's why this is the correct radius for the compact boson. Yeah, so I substitute this into here, right? Yeah. But then I should be summing over all possible winding configurations. So that means I'm summing all possible integer n. So if I sum over all possible integer n's, remember that the path integral is e to the s, right? Yeah, sorry, e to the s, so, because I'm working with Euclidean signatures. Sorry. Yeah, so if we sum over n, then that tells us that this has to be 2 pi times integers. Okay, it's just like a Fourier transform, Good. Okay, so the reason why I go through all this is that now we have a different formulations of compact bosons in terms of a different field. And Now let's ask, what is the symmetry in this presentation? So since it's the same, sorry?
Is this duality for the the CFT is true only on the torus then, or can you then put it on any manifold and it's still true?
It's true on every manifold. Yeah, it's true on, it's exact duality that's true on every manifold. Sorry,
Yeah, how do I see the argument for the compact theta if I don't put it on a torus?
if you. Oh yeah, that's right. Yeah, I forget. Yeah, so there was a question that whether the duality holds true beyond just torus. So the answer is that it holds true beyond torus. And so when I define a theories, you should be able to put it on every manifolds. Okay. So I put it on torus is just a quick way to show that it's periodic. So a better way to show that the two theories are the same is to just write down all possible operators and compare them, their correlation functions. Okay. Was there questions? Oh, you asked, did we use a periodicity in time? Yes, we did. So here, because this is an integral of partial t theta, right? So then if you integrate over time, then this is basically theta at this point minus this point. But they are the same points, right? So then they can at most be differed by 2 pi times integers because of this periodicities, okay? Any more questions? Okay, good. So, yeah, so we went through this presentations. Now, let's ask, what is the symmetry in this presentation now? So, of course, it's the same Lagrangian as before. So we will have, again, a U1 symmetry. But now I'll call it a U1 winding symmetry. I'll come back to it. So what symmetry is doing is shifting theta by some constant, okay? But this symmetry, if you think about it, this symmetry actually only acts on theta. It's a symmetry that does not act on phi x. So there's a kind of symmetries that was there that acts on the dual compact bosons, but not on the original compact bosons, okay? And there's another symmetries. Of course, it's a charge conjugation. So this is the same charge conjugation as before, the shift theta, the flip thetas, okay? So this is the same charge conjugation as before, okay? So this is an example where we see that if we just consider symmetries as an actions on the field, some path integrals, we might miss some symmetries, right? In this presentations of writing compact boson in terms of phi, we only see this symmetry manifestly. But these symmetries will be manifest if you go to dual presentations, okay? So this is the reason why we see different symmetries in different duality is actually the flawness of formulating a quantum field theories using a path integral. So symmetry should always be preserved across dualities. In particular, global symmetry has to be preserved across dualities. Yeah. Yeah, that's a good question. So charge conjugations here flip phi to minus phi. So in particular, that means that we will flip x mu to minus x mu, right, using the top equations. But then if you flip x mu to minus x mu, then it flips theta to minus theta, okay?
Those things are only at the level of equation of motion.
Yeah, but they are identified as operators. Like if you write operators using theta and phi, that's how you relate the two. Yeah, that's right. Good. So this is an example that shows us that we should think about symmetries more invariantly, not just in terms of how they act on the fields in a path integral. So let's now talk about how we can formulate symmetries more invariantly, independent of the presentations of the quantum field theories. Okay. So the idea is basically, remember that when we think about quantum field theories, we can always think about this as a set of operators. And then we can talk about the correlation functions and so on. So now let's talk about how to invariantly formulate a symmetry. So let's first start with the U1 symmetries that we saw with. So since this is a continuous symmetries, so then there's another theorem that we can assign to the symmetries, or we can derive using the Noether's procedures. So for the U1 shift symmetry, the current, we can just use the Noether's procedures. It's given by the derivative, the functional derivative of the Lagrangians with respect to partial mu phi. Okay? Then it will look like I r squared partial mu phi. So here there's a I that appears. It's just because I'm working with Euclidean signatures. Okay? And this current is conserved. Why is it conserved? Because of the equation of motion of phi. Equation of motion of phi tells us that Laplacian of phi vanishes, which is basically the current conservation equations. Good. So what about the U1 winding symmetries? So the U1 winding symmetries acts on the fields in a different presentation. So we can write it in terms of using Noether's procedures. So then if we write it down, it looks like I over 2 pi r squared partial mu theta. Okay? And we can use that relations of dualities to translate it back into the equation, into expressions in the original expressions in terms of phi. Then this is given by minus 1 over 2 pi partial mu partial nu phi. Okay? So one can check that this is again a conserved equations, conserved currents. But why is this current conserved in this presentation? This current is conserved because of the Bianchi identity, because there's an epsilon tensor sitting there. So this is conserved not because of the equation of motions. This is conserved because of the Bianchi identities. So in a sense, this is guaranteed to be conserved because I'm constructing the currents using epsilon tensors. Okay? Yes, yeah, I should do it the other way.
So you can only define this epsilon tensor in 2D space-time dimension.
Oh yeah, so the question was about, let me just repeat the question. So the question is about the indices. So that's, and then the point is that I'm just talking about 1 plus 1 dimensions. So there's an epsilon tensors defined in 1 plus 1 dimensions. So that's why we can do these contractions. Okay. So that's why epsilon tensor only have 2 indices. So if we work in different dimensions, then epsilon tensors have different set of indices. Okay. So this gives a way to formulate continuous symmetries more invariantly. We just need to look for Noether's currents, and then we need to, if this Noether's current is conserved, then we say there's a symmetry. Okay. So from a current, then you can also construct some more objects associated with the symmetries. So this includes, for example, the conserved charges, as well as the symmetry operators that implement the symmetries. So what are the conserved charges, and how do we construct them? So let's talk about conserved charges now. So the conserved charges, oh yeah, there's a question. Oh, sorry. You said it doesn't take the sound correctly?
I don't know if it's just me, but I feel like there's some like rustling.
Oh, I see. Okay, I don't know whether it's better. Yeah. Okay, yeah, we'll find out. Yeah. Good. Yeah, maybe I'm just moving around too much. Yeah, that might be the reason. Yeah.
I think in defining the Noether current, the first current is only conserved only for the on-shell solutions, but the second is conserved even for off-shell configurations.
That's correct. Yeah.
Do you have a comment on that? It seems that they are not conserved at the same level. The second one is more.
Yeah. So.
In some sense, more conserved.
Yeah. So the things that we really care about is actually this equation. It's if we insert this in correlation functions. Okay. Yeah, so in fact, you're allowed to insert a bunch of other things, and then this has to be 0. So that's the statements of current conservation equations. Okay. So we just need it to be true on shell in correlation.
So it's like saying since we always quantize the theory upon its solutions. So that's why in that sense that it's still kind of all the currents can be treated at the same level.
That's right. Okay. Yeah. That's right. Yeah. That's right. Any more questions? Yes.
So, I mean, improvement terms are something that I can always add to a Noether current. It's always guaranteed to be conserved by construction. Would you say that, if I just write down an improvement term, that's just that gives you another symmetry.
That's right. So the question is about improvement terms. That if we give me occurrence, I can always improve it. So what does improve? What does improvement mean? Okay. So say I have a current that obey the current conservation equations. Okay. So I can always redefine the current so that it still obey the current conservation equations. So what I can do is that I can shift the currents by something that's built from the epsilon tensors. Okay. Something like this. Okay. And then this still gives us a conserved current. So this is what's called the improvement of currents. And then one may say, well, this improvement is precisely what I do here, right? Then one may say that we can just do an improvement to get rid of this, okay? But that's incorrect, because when we do improvement, what's happened here is well-defined operators. But here, phi is not a well-defined operators. It's a field that has a periodic field range, so it's not well-defined, okay? So that's why you cannot remove it by improvement. And in fact, this is a very important point that tells us that the notion of current is not very well-defined. So what's well-defined is, in fact, the charges. So I'll come to that later. Okay, there was another question.
Yeah, maybe a follow-up on the previous question is, I guess if we started off working in the theta picture and then did a duality transformation to phi, we would have said that the second current is conserved on shell, whereas the first current is conserved off shell. So from that point of view, I guess, why is one maybe quote-unquote more conserved somehow than the other? Yeah, so the both are equally conserved. I'm not saying that they're different. Yeah, it's just they're conserved for different reasons. Okay. Yeah. Okay. Good. Any more questions? Good. Okay. So let's now talk about conserved charges. So what is conserved charge is basically given by integral of the time components of currents integrate over the whole spatial slice. Okay. So this is actually important points related to the questions about improving currents. So if you try to improve the current, then what happens is that you're shifting this thing by itself plus partial x alpha dx. But because alpha is a single valued operator, so this thing vanishes. Okay? So this tells us that currents has suffered from this ambiguity of improvement, but then the charge is actually well defined. Okay? So this charge is conserved because of the current conservation equations. So what does it mean a charge is conserved? It means that it doesn't depend on time, right? So its time derivative should vanish. So its time derivative vanished because if I act partial t on J0, we can replace that by the current conservation equations. Now I is just indices over the space, okay? And this thing's vanished. So that's why this charge is conserved, okay? So from a conserved charge, we can build a symmetry operator. So what is a symmetry operator? A symmetry operator is something that is exponentiations of the conserved charge. So the symmetry operators are important because they are basically the things that implement the symmetry transformations. Okay. And let me make one comment is that so the symmetry operators are parameterized by alpha, which is the symmetry parameters. And remember that alpha is actually 2 pi periodic. Okay. So this is 2 pi periodic only if the charge is take integer values. Okay. So for U1 symmetries, the charge are integerally quantized. Good. So now we have symmetry operators. Let's talk about how it acts on states and operators. So let's now work in Hamiltonian formalism. So in Hamiltonian formalisms, we have the operators. Then what it does is that it will map a state into a different state by acting this on the states. Okay. So this is how we transform a state. And then it also acts on operators by conjugated actions. So in a sense that these symmetry operators are more fundamental because they are the things that actually implement the symmetries instead of the charges. So even though charges, both charges and symmetry operators are conserved, but charges actually doesn't implement symmetries. It's the symmetry operators that implement the symmetries. So a consequence of this being a symmetry operator is that
it should live a Hamiltonian invariant, okay? And since this lives the Hamiltonian invariance, then you can show that this operator has to be conserved. Why? Because the time derivative of the operator is given by its commutators with the Hamiltonians by the Heisenberg equations. And from here, you can see that the fact that the Hamiltonian is invariant tells us that the symmetry operators and Hamiltonian commute with each other, okay? So that's why this vanishes, okay? So this tells us that both the symmetry, both the conserved charges and the symmetry operators are conserved. Okay. Good. So let's just recap what we have said so far. So we have reformulated the symmetries in terms of conserved currents, charges, and symmetry operators. But this is just for continuous symmetries. What about for discrete symmetries? Remember that we also have an example of discrete symmetry, right? That we have this charge conjugation symmetries. So how do we formulate charge conjugation symmetries using this language of operators? So just to recap, U1 symmetries correspond to a whole set of things: a conserved current, a conserved charges, and symmetry operators. Okay? But you see, if I have a discrete symmetries, I wouldn't have current for me. I also wouldn't have a charge to talk about. So the best I can do is that I can assign a symmetry operators to a discrete symmetries. So an invariant way to formulate symmetries is to talk about a set of conserved symmetry operators. Okay. So let's now talk about how we will formulate charge conjugation symmetries. A charge conjugation symmetries is basically a conserved symmetry operators, which is Z2 ordered. So if you multiply this operator against itself, then you just get identity. So this is what you mean by having a Z2 symmetries. Okay. So we should think about symmetries as a set of conserved operators that are labeled by some group elements assigned to the group. Okay. Any questions? Good. So now, oh yeah, please.
Why can't I talk about charges? Z2 you have 1 and -1. Well, why isn't it well defined?
Yeah, so the question is that why we cannot talk about charges. For Z2, it seems like we can assign +1 and -1. So what is the assign +1 and -1? You're not assigning charges. What you assign is the eigenvalue of the symmetry operators. When I say charges, I specifically mean something that lives in the exponent of the symmetry operators. Okay. So we can assign eigenvalues of symmetry operators, and that is conserved. Any more questions? Good. So I told you about symmetries. Now let's talk about the actions of symmetries on operators. So what are the operators charged onto the symmetries? So I told you that the winding symmetry actually doesn't act on the field phi. So in what sense this is a good symmetry? So let's talk about the operators that charge under a symmetry. Okay. So I already mentioned that phi is not a good operator, right? It's a field with a periodic field strength, so it's not well defined. So phi is out of game. Let's talk about operators that are well defined. So operators that are well defined include, for example, derivative of phi. So this is well defined because it don't suffer from this periodic identifications of phi. Okay. So this is well defined. What else is well defined? The exponentiation of phi is well defined, but this is well defined only if this exponent n take integer values. Okay. And what else is well defined? We can also define similar operators using the dual field. So this also has to be integer quantized. So these are some operators that are well defined, and then we can talk about how symmetry acts on these operators. So in particular, what happens is that the U1 shift symmetry acts on this, but not the rest. Okay. So when we sandwich this between the symmetry operators, we get a phase. So similarly, for the winding symmetries, this is charged only under the winding. So for this operators, this is only charged under. This is the only operator charged under the winding symmetries. Good. Okay. So here I give you how this operator look like. But one thing you may ask is that this is there's a duality that connects phi and theta, right? So how can I express these operators in the original expressions in terms of phi? How do we even define this operator, talk about these operators? So since we don't have theta in our hand, so we cannot just write out a simple expression like this. So the way to define this is invoke this idea called disorder operators. So now we're trying to define an operators in the original expressions, in our original duality frames written in terms of phi. So let's talk about what is the invariant meaning of these operators. So the invariant meaning of this operator is that this is an operator which is charged under the winding symmetries. And what is the winding charge? The winding charge is basically given by the integral of theta, of phi, okay? So it's measure how much phi winds around. So that means that if I have these operators, if I measure the winding here, I find that there's no winding. But if I measure it after this, I find that there's a winding, okay? So that means that the way we can think about this operator is that we can think of it as an operator that is defined as a singularity in our path integral. And this is the operators which is characterized by a property that if we go around this, we find that the phi actually winds around. So it's sort of like a vortices, okay? So it's a vortices. So the defining characteristic of this operator is saying that, let's work with polar coordinates, okay? Is that this operator, if we go around this, we will find that the field phi actually winds around. And its winding is given by 2 pi times n, where this n is the n that appears here, okay? So this is a way to define these operators using some singularities of the path integrals. But this also points us to something interesting. That is, remember that the currents that I wrote down is conserved simply because of the Bianchi identity, right? But you can ask, what if I write the similar currents for a non-compact boson, okay? But if I write the similar currents for non-compact bosons, it is, of course, conserved, just because of Bianchi identities. But now, there are no operators that can charge under the symmetries. Because remember there, what happens was that when I go around the vortex, my phi actually winds around. That is allowed because my phi field has a 2 pi periodicity. But for non-compact bosons, my phi field has to come back to exactly itself. So that means that there are no operators that are charged under the symmetries. So this means that even if there's a conserved currents, it doesn't mean that there's a symmetries, because we need to check whether this symmetry actually acts naturally on the Hilbert space and whether there are operators charged under that. Okay? Okay, good. Yeah, a disorder operator, you can think about it as defined by singularities of the field configurations. So here is a singularity in the field configurations in the sense that the field configuration winds around this. Yeah, so it cannot shrink properly. Okay. So, okay. So I told you how we can think about symmetries in terms of some conserved operators. But there's something we can do even better. So because we're working with Lorentzian quantum field theories, right? So that means that time is not a special directions. We can always pick it to be some other directions. We can do a Lorentz transformation to pick it into some direction. So that means that we should be able to define symmetries in a way that doesn't depend on how we pick time. So before we think about symmetry as some operators that are conserved in time, but now time is not the invariant meaning doesn't have invariant meanings in a Lorentzian, in a relativistic quantum filters. So that the way we should think about it is that we should define a symmetry in terms of something called topological operators. Okay. So the idea is that we have some notion of conservation in time, but now we want to replace this notion by topologicalness of the operators. So how do we do that? We have the current, right? But now I want to use the current to define a differential one form. So this is a current that we just contracted with dx mu. So this is defined for us a differential one form. Okay. And we can also take the Hochschild of this current. The Hochschild of this current is basically contracting this with a bunch of epsilon tensors. That's right. Yeah. Okay. So the reason why I want to define this Hochschild of the current is because now the current conservation equation actually is telling us something very nice about the Hochschild current. It's telling us that the Hochschild current is in fact closed. So it's a closed differential d minus 1 form. Okay. This is d minus 1 form. So let's look at the exterior derivative of that Hochschild current. It is basically given by partial mu, j mu, times a volume form. Okay. So the current conservation equation is basically telling us that the Hochschild current is actually a closed d minus 1 form. So then this gives us something pretty nice. So we can define now the symmetry operators not just on a constant time size. We can define it on arbitrary codimension 1 closed manifold. Okay. The reason why it's codimension 1 is because we want to integrate a d minus 1 form against some manifolds. Since this is a d minus 1 form, we can integrate it against a d minus 1 dimensional manifold, which is codimension 1 in space-time. So what is the operator? The operator is given by the exponentiations of the integral of the Hochschild of the current. Okay? And this operator, I'm claiming that this is topological. And what I mean by topological? What I mean is that imagine that you have some correlation functions involving both the symmetry operators and some local operators. So what I mean is topological is that I can deform these operators continuously, and it will not change the correlation function at all. So I can, for example, create a little dip here to move it from here to here, and this will not change the correlation functions. So that's what I mean by topological. And the reason why it's topological is the following. So let's call the original manifold M, the new manifold M prime. Then we can ask, what's the difference between M prime and M? Okay? So the difference between M and M is basically the integral over these regions, right? Over this region. They form a closed manifold themselves. Oh yeah. So yeah. So M is this whole things, the things, and let me write M prime more correctly. So M prime is these things. Okay. Yeah. So the difference between M and M prime is basically this part, right? I should probably use a different color. The difference between M and M prime is given by this part. Okay. But this is a closed manifold on its own. So we can write the difference in terms of an integral of E of star j using the Stokes theorems. So the difference between these two operators is given by integral of B star j in this region. Okay, which you can think of it as a region where its boundaries is given by the difference between M prime and M. Okay. Yeah, there's a question.
I'm a little confused about the U sub g versus the alpha in the exponential.
Oh yeah. So there should be alphas in this case. But I'm jumping between the two notations in the sense that eventually I want to label the symmetry operators using group elements instead of just alpha, which is so in U1 case, G will be exponentiations of alpha. Okay, so I really want to label them by some group elements. Yeah. So if you see G, just think of it as like there's a corresponding alpha. Good. So because this current is conserved, so this thing actually vanishes. Okay. So this tells us that these things will just be identity operators. So this tells us that the operator that we start with is identical to the operators that we end with. Okay. So an operator is invariant under small deformations, as long as it doesn't cross any local operators. Okay. There's a question.
But this assumes J at different location commute with each other, so that you can sort of factorize their differences as exponential.
So the questions was about whether I assume that the J has at different points has no correlations.
Right.
So that was the question. So here is just a rewriting of the operators. I'm not so this operators, it's written as exponentiations of this integral, right? I'm just dividing the integral into two parts. And then
You cannot divide an exponential into two exponentials if the operator do not commute. That's my question.
if the operators do not commute.
Like exponential A plus B, when A
I see what you're saying. I see what you're saying. Yeah, that's right. I use locality, yeah, because one operator is supported on some manifold, and the other operator is supported on a complementary manifold, so they will commute. If you define it on a constant spacetimes, like if you define on constant spacetimes, right, that an operator defined here will commute with an operator outside.
Right, but that's a real-time picture. You are discussing Euclidean geometry.
That's right. So when you discuss commutators, that's only in the Hamiltonian formalism. So that's why I'm talking about this is a constant time size picture. So.
Okay.
So yeah, so I'm just expanding the operators. Yeah, if you think about this is an operator defined in path integral, so you don't care about their ordering. Yeah, it's just an operators in the path integral. Is there any more questions? Okay. Good. So the point is that now we can uplift the notion of conservations into topologicalness of these operators. And let me explain a little bit why this topologicalness is the higher dimension, is a Lorentzian invariant avatar of conservations. Okay? So the idea is very simple. So here I define the symmetry operators on some generic codimension 1 manifold. But now let's just go back to connect with the Hamiltonian pictures. So if I define these operators as a constant time slice, right? Then this just reduces to the usual symmetry operator we talk about in the Hamiltonian pictures. This is an operator that acts on the Hilbert space. But the fact this is topological means that I can move the whole operators out to a different time, right? This is a topological move. It's a continuous deformations. So that means that the operators that we end up with at a different time and the operator that we start with they're actually identical. So this is a statement that topologicalness implies conservations. Okay, so topologicalness is an uplift of the conservations of the operators. Good. So now let's talk about how we can think about the actions of symmetry operators on some local operators, on some point-like operators. So let's talk about the actions. So how do we define the actions of an operator? We define it as the following, right? That this is the new operators that we obtain from the symmetry actions. We define it as conjugating the operators between the symmetry operators. But if we think of it in a path integral language, it means that we first start by inserting the UG inverse operators, right? Then we insert the operator O. Then we insert the operator UG, right? So this is what we do if we want to do a path integral to represent these actions in the Hamiltonian language. And since they are UG and UG inverse, so let's just introduce some arrows to give them some orientations. Now what's nice is that this operator UG and UG dagger, they're topological. So I can deform them. So I can deform them so that I can close it up. So I basically have an operator O that is surrounded by a codimension 1 symmetry operators, okay? And since the symmetry operator is topological, so I can shrink it. When I shrink it, then I basically just obtain a local operator again, a point-like operator again. And that is the O prime operator, the O2 operators, okay? So basically, how a symmetry acts on the operators is given by linking. So we link the symmetry operators with the operators that we want to act on, okay? And this also means that if we have a configuration where we have symmetry operators, remember that I said I don't allow symmetry operators to move past any local operators, right? I don't allow that because that's not a continuous deformations. But let's see what happens if I insist to do that, okay? So I have a symmetry operators. I insist to move this operator past this local operators. What happens? So what happens is that we move the operator past, okay? But then when we move that past, the operator has to go through a symmetry actions, just like what happens there. So when we move a symmetry operator past a local operator, we basically implement a symmetry transformations on the operators, okay? So that's how we define the symmetry actions. Here's the question.
Why would you write UG as a plane?
You mean here?
Yeah.
Oh, sorry. So the question was about why I don't write UG as a plane. You mean here or you mean here?
Just like from the last word, it hasn't been like a topological thing.
The last word.
So UG of M, so M is a codimension 1 whole set. So I could imagine you write you represent it as a plane on the board, but then UG of M, how did you do that?
Oh, so you're asking, was the question that why I draw it vertically instead of horizontally?
No, just in any case, like, why is it a plane?
Why UG is a plane? Oh, I see. Yeah, so yeah, here I'm drawing this as if I'm in 2+1 dimensions. So then a codimension 1 manifold in 2+1 dimension is a surface, right? So that's why I draw it as a plane. Or some generic surface or something like a surface. Does it answer the question?
I just couldn't see it like say like you have the exponential I alpha integral.
Yeah. So.
J, like why is that saying a topological object yet?
Oh, you mean why this operator is topological?
Yeah.
Oh, that was what I was arguing here. So I was arguing that if I continuously deform these operators in space-time, deforming its shape, then the operators are in invariant deformations because of the Stokes theorems, using the fact that this J is a closed current.
I see. You were basically saying that it's similar to M itself?
What is similar to M?
UG.
UG. Oh, yeah, UG is the final M. UG is the final M.
Okay, thank you.
Yeah, I can answer that. Yeah, so there was a question.
So actually on that note, so in the left word you had defined U only on closed manifolds.
Yeah.
And now you're drawing on planes. So what sort of assumptions? It seems like you have to make some strong assumptions about what happens far away.
Oh, I see what. Now I see. I guess the question was about why I draw an open manifold instead of a closed manifold. That was the question. Okay. Now I see. Yeah. No. I draw. It's supposed to be a closed. Yeah. I take my space to be closed. Yeah. To be closed. Yeah. Or I can assume that the infinity die off, so then I effectively close it up. Yeah. So okay. So there was a question.
This might be related, but I'm confused when we went from 2 planes to a ball.
Yes.
Why we lost the UG dagger label?
Oh, that's a good question. So when I write UG dagger and UG, this is how we think about them in the Hamiltonian pictures, okay? But then we think about it in a path integral language, then all we care is about orientations of the operators. So this is an operator that has an orientation going down, and this is going up. So they are sort of the orientation reversal of each other. There was another question.
There's
So the question is did I assume that I'm working in a vacuum instead of a general states? So that was the question, right?
Vacuum sector, I think those two operators are actually the same, right?
Yeah, so the point is that I'm thinking about inserting these two operators into a correlation functions that can involve insertions of other local operators, okay? Then my claim is that these two operators are identical as long as the region, as long as this blue regions doesn't enclose any local operators. So that means that the deformation I do in space-time is a continuous deformation that doesn't cross any local operators.
Okay, I see. So that's the sense in which you are saying that these operators are topological, right? Because if you have operator inversions, that's somehow a defect.
That's right. That's right. Yeah, that's right. Okay. Yeah. Any more questions? Or?
Why you call it linking instead of like surrounding?
Oh yeah, that's a good question. Yeah, I'm a mathematician. No, okay. Yeah, it's just because it generalizes later. So this is an example where you have a codimension one. You have zero-dimensional objects that can link with a codimensional object. So what's happened later is that you can have a higher codimensional objects that link with a dimension higher objects. So that's the mathematics is called Hopf link. Okay. Yeah. Any more? Yeah, do it.
Sorry, I'm a little lost in the motivation. What are we trying to do here?
Yeah, so I'm trying to formulate. Yeah, that's good. That's good.
I'm sorry, because topology leads to conservation. We know that from Berry connection leads to Chern number, right? So what have we learned new about?
Yeah, good. Yeah. So I'm trying to formulate the symmetries more invariantly using some topological operators. So that's basically what I'm saying. So if you recall the examples that we start with, that if we think about symmetries as actions on fields, then there's some symmetries that we wouldn't be able to see, right? So we want to formulate symmetries more invariantly in terms of some operators. And then I want to claim that the property of these operators is that they have to be topological. So basically, topological operator is the definition of symmetries. Yeah. Is there any more questions?
Another question. So there you link the two planes for the sphere, closing the operator. Could you form that sphere by going through the operator with the bottom plane and going through the operator with the upper plane, forming a sphere, but at the orientation that it's pointing inward? Is there some duality between that?
So you want to? So the question was about orientation. So you want to swap the two planes, or
yeah, you close them by swapping, and then you get like a sphere with the opposite orientation.
Oh, okay. Okay. So that.
Duality there, or?
Yeah. So that assumes that this operator and this operator commutes, and then also you see if I want to swap these two planes, I need to move this operator out and this operator down, right? So I will need to cross these operators, let this operator cross the point operators. Okay, so that's not a topological. So this is the only allowed topological move. Okay, so let me just get to a punchline. So this is also there was a question about why we're doing this. So the question was, the point was that so now we can give operator definitions of symmetries. So what is a symmetry now? So a symmetry defined by a group G can be thought of. So one way you can do that is that you just take all your correlation functions and check that they obey some selection rule of some symmetry G, okay? But then there's an easier way. The easier way is that we just look for some codimension 1 topological operators. So once we found these topological operators, then we claim there's symmetries, okay? But how do we know the information about the group? So information of the group is encoded in the label of the symmetries. So these symmetries are labeled by group elements of G, okay? And then the way we can read off the group is that we can now take two operators and try to fuse them. So we can take an operators labeled by UG and an operator labeled by UH, okay? Then we can fuse them, then we get an operator UG times H. So by looking at how the operator fuse, we can read off the information of the group. So the fusion is basically a group it's a group multiplication fusion. So this is how we can encode the information of a group. in this symmetry operators. Okay. So this is basically the punchline that we should think about a symmetry in a more invariant way using a set of codimension 1 topological operators. There was questions? Yeah.
What dictates whether G or H is going to come first in a subscript that's used operator?
That's a good question. So So the question was here I draw it this way, and then I write that it's U G times H instead of U H times G, right? So I intrinsically actually define an orientation in these operators, okay? So all this operator has an orientations. And so the way I draw it is convenient because you can think of it as time. Then this is like I first add an operator UH, then an operator UG, and then they give you UGH. Okay. Okay. Yeah.
So would that be a factor? So if the UG, if I do good multiplication UG times UH, would that be an extra factor, the phase factor, multiplied in front of the UGH?
Oh, you mean is it possible that there's some phase factor here?
Yeah.
Oh, okay. That's a good question. So in this case, the phase factor can be redefined away. So we can redefine that phase factor away. Yeah, it's just absorbed into the definition of UGH. Yeah.
What exactly is the fusion operation there? Like we have two topological operators. What do we do to get a new one?
The idea is let's draw. So the question is that how to define these fusion actions, right? So let's draw some pictures. So let's first say we have a picture like this where we act UH first, then UG. Okay. So now we can imagine that we take an operator's past this line, move it down. Okay. So we just move it down, and then we try to, because there are two topological operators, so we can bring them very, very close. Then when we bring them very, very close, they should define another topological operators. So that's how we define this fusion actions. Okay, because they are topological, we can bring it close. Yeah. Does it answer your questions? Okay. There was
kind of related to that is like more in an equation. It's going to be something like you're going to have some structure constant of the G. You have UG, UH, and you're going to have some structure constant with some other group element.
structure constants. What do you mean?
It's going to be like some rule like the commutator or UG, UH on the left-hand side. It's going to be given by like structure constant GHK over UK. I'm not sure if it's there. Like an OPE kind of thing.
So the question is that whether there's a structure constant that appears in the fusion?
Yeah.
Yeah. So the way you should think about this equation is basically just if I add UH first, then UG, then this is in Hamiltonian language, it's just UGH. Okay. So that's the way you should think about this.
But I guess
there's no
GH is some group element to be like expanded using the structure constant.
Oh, I'm just labeled them using group elements. So there's no. I'm not talking about them. I don't expand them into exponential I5. I don't do that. I just talk about group elements. Yeah. So there was the questions. Yeah.
So I guess the first one is okay. So a general question, I guess, for conceptual understanding is my understanding is you were for most of the lecture talking about conservation, these topological operators, and then you wrote topwise conservation, and then my understanding is now you're saying that combining these two, we can give an operator-based definition for symmetries. And I was just wondering if you could maybe say at least the most important assumptions that we need to go into that, or like when does this apply?
So the question was about I derived the symmetry, topological symmetry operators using the current conservation equations, and then was a question that.
Oh, my question is like this claim that like symmetry equal code dimension one topological operators. Like how general is that? Like when does that apply?
Oh, this is a general definitions. Yeah, this is how we should think about symmetry in terms of operators.
I guess we'll see that generalized symmetries can involve other codimension operators.
That's correct. Yeah.
So like
yeah.
this applies in some like a wide variety of cases.
Yeah, that's right. Yeah. So like if you so before I talk about there are two symmetries, right? That they have different actions on fields. So both symmetries actually lead to some topological operators. Yeah. So that's a way to think about symmetries, that there are some topological operators, and then we don't care about their actions on fields. It's just some topological operators, and then they can act on some local operators.
Just to let you know, we have about 7 minutes left.
Yeah. I think I'll just wrap up here. Yeah. There's one more question. UGs? Oh, yeah, so this is how I define the fusion. The fusion is given by the group multiplications. Yeah. Sorry, there was a question.
So will we be able to distinguish with this language the symmetries whose currents were conserved because of the equations of motion or because of Bianchi identity?
Yeah, so no. So the point is, that's actually the point. So the point is that current conservation equations is equations. You don't care about how it comes from. It can come from equation of motions or Bianchi identities. In fact, if I change the presentations from the phi to thetas, then I actually change how the current conservation arises. So the key is that those current conservation equations will always lead to some topological operators. Yeah. Here's a question.
How do you, is UGH on the right hand side of the same type of operator as UG and UH, or how do you see that you don't get some of different operators? If you do a P in a CFD.
Yeah, that's a good question. So if you go back to a continuous case, you remember how the operator is defined by alpha, right? So if I now literally take two operators, alpha and betas, and fuse them, then I basically just need to sum over alpha and betas. So I get an operator that is alpha plus beta, okay? But alpha and betas are not group elements labels. So the group element labels are exponential I alphas, exponential I betas. So this tells us that we are labeled by exponential I alpha plus betas. Okay, so this is really group multiplication. Yeah. Okay.
So I think I understand the story when you like fully fuse UG and UH, but in this picture where you've like partially fused them, what kind of degrees of freedom live at the junction between them?
That's a very good question. So in principle, you can define some phase and things like that. So there could be some ambiguities in the phase. So, but then that is a freedom that you can pick. So that's there's a freedom of phase that you can assign. So yeah, that's a freedom. Yeah, but at this moment, it's just a topological junctions where you bring two operators and then it gives you the third operator. It's a topological junctions between the three symmetry operators.
I'm going to suggest we let Ho-Tat just get to his punchline in the last few minutes.
Yeah, this is basically the place I would like to stop. Yeah.
Okay,
Yeah,
then in that case,
guess,
ignore it.
Yeah, I guess. Okay. Yeah, I can just take questions now and then.
I think you might have actually already covered it, but I don't think I caught it at the time. Is all this just holding inside of correlators?
That's right. All of this are holding inside correlator. That's right. Yeah. The question, just repeat the question. The question was about whether the equations that I wrote down are equations that are holding inside the correlators. Yeah. So there was another question.
Yeah, so from these rules, it seems like UG on M is equal to UG inverse dagger on M, right?
UG. So the question was.
You're all unitary. UG
of M is UG dagger of M.
Yeah,
G inverse. Oh yeah, that's right. Yeah, that's right.
Is that also equal to UG of minus M?
UG.
This orientation, like reversing orientation of M, does that give you the U dagger?
That's correct. That's correct. So you should think about. So the question was about orientation reversal. So if I have UG of minus M, where the minus means that we change the orientations, then they should be thought of UG dagger. Yeah. That was the question. Yeah, that was. I haven't get to higher from symmetry. Yeah, it's slower than I thought. Yeah, it's unfortunately slower than I thought. Yeah.
I have a follow-up question on what Matt leave on that junction. It looks to me that this U furnishes a representation of the group, but could it be a projective representation where it's up to a phase, like e to the I some phase, depending on G and H?
Oh, okay. So the question was that I talk about these fusions, and then the question was that whether there could be some phase that appears so that the action is projected.
You mentioned there could, in principle, something that lives on the junction.
That's right. Yeah. So the question was that whether the symmetries can act projectively. So that's a very good question. So that question was connected to the notion of anomalies. So a symmetry is when it acts on operators, it always acts linearly. Operators always form linear representations under the symmetries. However, if you work in quantum mechanics, a state has phase ambiguity. So that means that when we define the actions of a symmetry operators on a state, on Hilbert space, there could be a phase ambiguity. So that means that the symmetry can act projectively on Hilbert space, and that's is connected with this notion of anomalies. Yeah, that will come later. Actually, yeah. Okay. Yeah.
Just a question. So in the old school interpretations, gives me some operators. But if you just told me use a Lagrangian to find all the codimension 1 topological operators, I mean, I do know this theorem, but then I wouldn't know how would I get any more? Like, is there any general methods to know how to actually get these things?
That's a very good question. So the question was about if you give me a Lagrangians, I can identify some symmetries by their actions on fields. And then I can use that to identify a set of topological operators. But how do we know that's the complete set and whether there are some systematic constructions of all the possible topological operators? So here, actually, that's an example where just by looking at symmetry actions, we wouldn't be able to see the other symmetries, right? We have to use dualities to see the other symmetries. So that's actually a question of art. So you can say, what is the property of a topological operators? The way you should think about a property of topological operators is that it's an operator that commutes with stress tensors. So basically, you need to solve the equation, solve conditions where you have some operators that commutes with stress tensors. Okay. So there was a question. Maybe I'll take it as a last question.
Kind of following up on that, if you have some set and you want to see if it's complete, could you just try doing this fusion and see if you get something still within the group?
That's right. Yeah. So if you have some operators, you can keep fusing them. Those operators are guaranteed to be topological. And then so that's a way that tells us that you can identify all the symmetries that form a group. Okay. But then it's possible that there's some other groups that you don't see, like just using like the conventional actions on fields. Okay. So actually, let me just conclude here, and then I'll just give a sort of advertisement for next lectures. So this is about ordinary symmetries, how we can think about it as some topological operators, and then this formulation actually gives us a very natural way to generalize to what's called higher form symmetries. So higher form symmetries are basically symmetries that has higher codimensions. Okay, and since they have higher codimensions, so then the things that they link with are not point operators. The things that they link with are extended operators. Okay. So that's the entry point. So that's a way to get to high form symmetries. I'll just stop here. Thanks.
Okay, so before we break for lunch, I want to introduce a couple more people to you all. Could I have all of the high energy theory CU grad students stand up, please? So the local CU high energy theory graduate students are here. They're happy to chat about local stuff, about a place you might want to go to eat, or also things about physics. But I just want you to know who they are. Could you just briefly say your names?
I'm Kenny Higginbotham. I'm Jade Citizen. I'm Rudy Rodriguez. I'm Johannes Reinking.
I'm Grace Marie Bueller.
And I think some of them have agreed to walk you over to lunch for the next stop. So the University Memorial Center is our student center. It's called the UMC. Everyone calls it UMC. That's where lunch is going to be. We'll meet back here at 2 o'clock for the afternoon session. All right? Thanks, Wait.
If you want to know where the climbing gym is, I'm going to make a stop by there before taking people to lunch.
Yeah, I heard that. I heard a question, can you leave stuff here? I'm not sure I would leave valuable electronics here. I don't think there's anyone going around stealing stuff, but I would, if you want to leave your jacket, that's probably fine, but I wouldn't leave valuable stuff.